Good afternoon, everyone. Welcome back from lunch. I'm glad everybody managed to find this particular room, being downstairs and away from absolutely everything else. Thank you and welcome to Reactive Relational Database Connectivity, which is surprisingly not something I say very often. Normally we refer to it as R2DBC. So my name is Ben Hale. I am officially, I am the lead of Java on Cloud Foundry. Cloud Foundry is sort of an enterprise PaaS thing in the world, but I'm also the lead of the project we're going to talk about today, R2DBC. And the reason I'm here talking to you about this, even though nominally I deal with, sort of a cloud platform, is because my position running, sort of the bit of the organization at Pivotal that focuses on Java workloads on something like Cloud Foundry has given me a really unique sort of visibility into the problems and the needs that enterprise Java developers actually have. And clearly one of the most important needs and problems that they have is they really don't like paying Pivotal as much as they are. And so a lot of these customers are starting to look to reactive programming as a way not to make individual applications faster, but rather to make their individual applications a bit more efficient. Not a bit more efficient, that's really understating it, significantly more efficient. So we're going to talk about, first off, reactive programming. So how many people in here sort of practice reactive programming today, have actually written applications in it? Okay. So a good number of you, but by no means the entire room. So let's talk a little bit about what reactive programming is. My personal opinion, although it's certainly shared by sort of the Spring teams and Project Reactor, which is hosted sort of in the same group as well, is that reactive programming is the next frontier of high efficiency applications. So when we talk about reactive programming, what we're talking about is a programming model that is fundamentally non-blocking. Okay, this idea that when a reactive program needs to wait on something, whether that's a piece of data coming over the network, a piece of data being returned from the database, it doesn't occupy the thread in the way many of us are used to, especially if you're comfortable with programming against something like the Servlet API. The Servlet API, anytime a request comes in and you go off and you do something in your application, but in a microservice world, it's quite likely you're going to call out to yet another microservice. The whole time you're waiting for that other microservice to respond, nothing happens, right? You are going to occupy a thread, and as we've seen a couple of times mentioned today in various sessions, occupying threads it's very, very heavyweight, tons of memory dedicated to them, and there's a very small number relatively that can exist inside of a JVM. So one of the key things to take away from this is reactive programming talks a lot about non-blocking kind of behaviors, but doesn't actually have an opinion on whether or not those behaviors can be asynchronous or need to be asynchronous. In general, these two things are paired together quite a lot, right? So it's totally possible to wait and come back simply inside of the same thread or execute a number of steps inside of a reactive application without ever moving on to another thread. And this is typically the most efficient way to deal with reactive programming. And so frameworks underneath the hood will oftentimes do optimizations to guarantee that you sort of execute on the same thread as much as you possibly can. But we often pair this with an asynchronous kind of behavior for things that take a really, really long time, like going to a database or another web application. But one of the key differentiators when we talk about asynchronous programming versus reactive programming, because you can see they sort of play in the same realm, right? That the kinds of things you're trying to achieve are very similar to one another, is that reactive has this idea of what we call pull-push back pressure, reactive back pressure. And the key idea here is that as a consumer of data, I don't want, we would refer to that as a subscriber, I don't want a publisher of data, the supplier of that same data, to send me more data than I can possibly handle at any given time. Okay, we see this a lot today where, sort of you make a query to the database and somehow it's going to return you 100 million rows because something's gone wrong. And you can fill the TCP cache, you can send a bunch of data, fill up some sort of buffer internally inside your JVM until it exhausts your heap and the whole thing falls over. So reactive programming, whether it's inside of a single JVM or whether we're trying to connect over the network, its entire goal is I can make a connection to you, but I'm going to say, hey, give me the next 8 things. And you can only send me 8 things. If you need to send me 1,000 things, you have to wait for me to come back to you and say, hey, I'm ready for the next 8 things, or the next 128 things, or some size that the consumer decides it can handle. And so that's a big differentiator when you start seeing APIs talk about just asynchronous versus where we think the industry is heading, this sort of step beyond it, that's pull-push back pressure. So the Spring team itself has been talking a lot about reactive programming for 3 or 4 years now, and one of the key places that it's really shown up for most applications is in the web tier, breaking this single connection, single thread linkage that the Servlet API gave us many, many decades ago at this point. And what does this look like? Well, in this particular case, we're using a reactive framework called Reactor, Project Reactor, which is tightly affiliated with the Spring team, but the same kinds of concepts you see here would work if you're familiar with RxJava or something like that. And what the goal is here is to have a single web endpoint called /health, and we want to go off and we want to return the health that is a composite of 2 other microservices, basically acting as a proxy and compositing for these things. So we're going to say monozip, I want you to do these 2 things together, and the 2 things I want you to do is go talk to our alpha service here, retrieve the data from its health endpoint and turn it into one of these health objects, go grab it from our Bravo service as well, composite those 2 things in a tuple together, and return whatever that health object is that comes out the other side. But the key thing that happens here when you take a look at this code is you haven't described it anywhere, but these 2 things get to execute in parallel with one another. The calls go out at the same time, they wait, and as one returns, it'll obviously return faster than a second one. The second one eventually comes back in, and there's an automatic trigger that now we want to go to this map line, turn it into this composite health object. And the key, and during the waiting for these 2 things, it is not occupying the thread where you made a request for this composite health. So what effectively this means is in the web tier, during times that we're doing all of this kind of waiting, we get to more efficiently use that thread. It means some other request can come in asking for a different endpoint or this endpoint and occupy that thread. And so now where we see this pattern of really horizontally scaled applications, 10 instances, 25 instances, that all have sort of ticking along at 15, 20, 30% CPU because they can't get any more connections into a servlet container. Tomcat by default sort of does 200 threads and connections. You might bump that if you're really, really aggressive to say 2,000, if you've got a big memory space that you can work with. But fundamentally, the way a reactive web tier like this, Webflux out of Spring works, is that once these things start waiting, we can handle another request coming in. We're not tied connection to thread, and we can handle huge numbers of connections, like 20, 30,000 simultaneous connections, and we typically only do it with 4 threads or 8 threads. It's typically the number of threads that back your number of physical threads on your CPU. And now all of a sudden, instead of seeing this massively horizontally scaled application that is connection bound but not CPU bound, now we see sort of CPU usage in the 90 to 100% range on many fewer instances, but sort of handling the same sort of connection load. So there are still some barriers, however, to using reactive programming everywhere. I put a little star there. Speaking for myself, not as a member of Pivotal, not as a member of the Spring team, I love reactive programming. It's the only way I do it. I think in sort of the medium-term to long-term future, all programming will be done in a reactive way. The efficiencies gains and sort of as we move as an industry towards more functional-like languages, reactive programming isn't truly functional, but it's very, very similar. I think that there are. I think that we'll all eventually get there. That being said, that's not why I'm here today, to advocate such a thing. Let's, instead of saying reactive everywhere, let's say reactive everywhere that you think it's appropriate to use it. There are still problems that prevent you from doing reactive programming. So one of those things is cross-process back pressure. We say cross-process, but really what we mean is across a network. We're working with a couple other companies on a standard out in the world right now called RSocket, and RSocket, I've actually got another talk there that is not actually at this particular conference, working on RSocket to solve this kind of issue. It's sort of a replacement for HTTP, which allows you to do asynchronous messaging with the same kind of pull, push, back pressure, and demand and things like that. But by far, the biggest impediment most of the community has around using reactive programming is data access, right? Reactive data access, in some cases we already have it. MongoDB, Cassandra, Redis, sort of NoSQL kind of databases have sort of embraced this non-blocking, asynchronous kind of API before reactive even came on the scene. They sort of were built with that kind of programming model natively. But for a long, long time, we've not had relational data access. JDBC is a blocking imperative API and can't be used in a non-blocking asynchronous kind of programming environment. So, given some spare time stuck in my mother-in-law's house and not wanting to spend any time with her, I invented a project called R2DBC. It originally started, a guy named Ali Gurki, who's the head of the Spring Data team, sort of mused in a meeting once, I wonder what a reactive JDBC API might look like, and I just decided to take a look at what that would be. And so fundamentally, what we're talking about is an API designed from the ground up for reactive programming, okay? So R2DBC has a couple of really key design principles. Number one, and obviously the most important thing if you're trying to design a replacement for a very well-used API that already exists, we want to use reactive streams types. So I talk about Project Reactor, I've talked about RX Java, you could talk about something like Akka if you wanted to in the Scala world. All of these things are sort of joined together by a project called Reactive Streams. It's a very small specification. It defines exactly 4 types, a subscriber, a publisher, a processor, and I can't remember what the 4th one is. Clearly you don't use that one very much. And those types are it. It's an interop between all of these things. But the key is this sort of publisher subscriber with pull, push, back pressure. We want to use those kinds of types as part of the API. We want our implementations of this API to be completely non-blocking all the way to the database, including potentially using wire protocol. So I'm very familiar with the Postgres wire protocol. There are a bunch of other databases that have different wire protocols, but in there, for example, Postgres has this thing called a portal that effectively, in the wire protocol, in the framing for the wire protocol for Postgres, they have this idea of go get me the next 10 things and don't send me any more than the next 10 things. Or I'll tell you I want 10 things and you can return me 3 now and 7 later on if you want to. These are sort of built into the wire protocol miraculously already. And so where we can, not only do we want non-blocking all the way to the edge of the JVM, we want it across the wire to the databases themselves. The third goal is to shrink the driver SPI to the minimal possible set of operations that would be implementation specific. So we only want functions, we only want methods on our SPI that are implementation specific. If it's something that behaves more or less exactly the same way across multiple databases, then we don't want that there. We'll talk a little bit about this, a little bit more in depth about some examples of this later on. And then finally, we want to make sure that the SPI itself enables a bunch of humane APIs, right? We say this is probably not going to be usable to normal humans, but we want a ton of humane APIs to be built on top of this driver. And a great example of this already exists in the JDBC world, right? Very few people use the JDBC API directly these days. They use Juke, they use JDBI, they use MyBatis, they use JPA, they use Hibernate, right? These are all humane APIs at different levels of abstraction built on top of JDBC. So we say that one of the JDBC's biggest failings was that the same API had to serve as both the humane API, because remember this is sort of 20 years ago, people thought JDBC API would be used directly, so it had to serve as both the humane API as well as the inhumane API for implementing things like JPA standing on top of it. And this gave us an API that basically nobody liked, right? Developers don't use it directly because it's such a giant pain to use, even as far back as me starting in the industry, early 2000s, we had something like JDBC template at Spring that sort of wrapped all of this stuff up because you'd never use JPA, or you'd never use JDBC directly. But the driver implementers don't like it either, because what you end up with is the driver implementers end up duplicating a ton of effort. Like they all have to implement this sort of question mark binding from JDBC. There are other places inside of the API where if you went to the Postgres implementation and the MariaDB implementation and the Oracle implementation, they will have effectively written the exact same code because they can't share between one another, but this sort of humane API requires them to do this sort of duplication of effort. So it was basically a waste sort of industry-wide. So we said, let's take a step back. what is the minimal set of APIs that we want to implement for a database driver, even if it means this is completely inhumane to do it. And we're going to talk about a couple of different types. There's sort of a connection factory type that returns something, and then the thing that it returns is a connection, and we'll talk about some stuff that follows on there. So given a connection, and you can sort of imagine where this is in the JDBC world, here's sort of the level, or here are the APIs that we think are both database specific and not duplicative across databases, right? So beginning a transaction, committing a transaction, closing the connection as well. We understand that batching is a thing that people do on databases and needs a first-class construct for that. Save points and rolling back transactions and things like that. 2 save points all are in there. Setting transaction isolation. But the key one that we're going to take a look at next is this idea of creating a statement, okay? Now, one of the first things you'll notice if you look at this and you're sort of familiar with the JDBC API, you take a look at those return types, and there are some weird return types on there. First off, publisher. As I said, Reactive Streams has this idea of a publisher and a subscriber. And so what we're effectively saying is here, I'm going to hand you a thing, and I will subscribe to it at some point in the future. Publisher void ends up being sort of a shorthand of saying you're not going to actually send me any data across this. What you're going to send me is a signal that you've completed doing something. So I'll subscribe to, say, let's say, commit transaction. And on that subscription, it'll signal you, okay, go do the thing that you were going to do in the database. Go commit this transaction in some way. And I will wait here in a non-blocking way until you're complete. And once you signal that to me, I'll progress on from there. And so that's why you'll start seeing these publishers all over the place. We'll see some more complex publishers that aren't publisher void a little bit later on. So inside of a statement, we have the stuff that you probably would recognize for taking an SQL statement with some sort of positional identifiers in there and doing binding to them. So we can bind given an object identifier. So if you're using something like Postgres natively, it'll be $1, $2, $3. If you're using MS SQL, for example, they use named identifiers. I think it's :name, :name, :name. And so you do a binding based on those things. We have an add so that you have the ability to effectively do what you see in a prepared statement with Java. In JDBC. So unlike JDBC, which had 3 different kinds of statements, it had statement, prepared statement, and callable statement, and I don't know what the difference between the 3 of them really are. We have a single statement that supports all of those same kinds of behaviors, and we'll see an example of this in a little bit. But the idea is that you can effectively create a parameterized SQL query and then bind in some things to its positional and then do another one and another one and another one. And then when you execute, what we see right here, it will send all of those to the database and execute multiple things, whether it's multiple insertions or multiple queries with different values in them and things like that. And then obviously we can also return generated values like generated keys and things. So the thing that's returned, this result object, you can find out how many rows were updated. You'll notice this is where we start seeing this sort of more complex kind of publisher of an integer. So we wait in a non-blocking fashion for the database to tell us, for example, how many values were, or how many rows were updated when we did an insert or something like that. And we see this map function on the result as well. And this guy, we'll see this in much more detail. This is sort of the meat of what happens, right? You get this result back, what you might call a result set in the JDBC world, and we'll then do a callback to a mapping function. In this case, it's a by function. There's 2 inputs to it. We'll give you row metadata, and we expect you to do some kind of transformation. So you can imagine getting some tabular data, a bunch of column values, and turning it into a POJO and returning that back out. And then finally, the 2 simple things that come from the row itself. Go get me the value out of a row, out of a column row. So now we can take a look at some code here. All right, so we've got this connection factory. We call it create against it. And now we're going to do what's called a flat map many. This is a transformation that says, okay, given this connection, I want you to turn it into basically another publisher. Right, so you're going to do something lazily at this point, and that publisher is going to return more than one thing. It's going to return n kind of things. So we take the connection, we create this statement, select value from test, and we execute it. Given the thing that comes back, we're going to map it. So we're going to say, given the flat map that comes, or the result that comes back, we want to map each row like this, row.get, and returning whatever the value is. And this, what sort of comes out the end, what you'd expect to be on the next line, is, in this particular case, we're using Project Reactor, so it's a flux, but effectively it is a stream of all of the rows, the value column out of each one of those rows. So now that we've seen the first bit of code, any questions so far? Yeah. Why is it flat map many? You'd have to sort of understand what the Reactor API is, but the key here is that ConnectionFactory.create creates a mono, not a flux. So what's the difference between these two things? The Reactive Streams API has this idea of a publisher, and a publisher just returns 0 to n things. It's basically always a stream. But what we've found that is in practice, beyond just sort of interop between two different reactive frameworks, there is a really useful differentiating between 0 or 1, or 0 or n, right? And so we have two concrete types, both of which implement the publisher interface. One is a mono, one is a flux. So ConnectionFactory.create always hands you 0 or 1 connections, and then we have to get from that, here is a 0 or 1 thing, to a 0 to n thing. So flat map many just guarantees that it returns a flux of those values instead. Yep. I don't want to, I realize there's a lot of stuff going on in here, and Project Reactor is sort of its own thing as well that you're probably seeing for the first time. Yeah, so another question in the back? Yeah. Sure. So if we had done select star from test or something like that, right? Like, so there'd be multiple columns. Or are you asking for a single value that has all the rows in it? Yeah, okay. So one of the great things about reactive programming, when you see it, and like, again, this is really dense stuff. There are a ton of curly braces. There sometimes are a bunch of curly braces. In this case, there's certainly a lot of parentheses, is that you sort of deal with very functional atoms. So what we would typically do if we wanted to say for all of the rows that were possibly returned from this, the value out of all of them, we wouldn't try and do anything special here. We would do the same kind of processing where we mapped each result that came out of it, and then we'd match each row out of the result. And then what would follow after this is another operator. And so in the Reactor world, this would be .collectToList, for example. And that would then turn us back from a flux of whatever this is, integers, strings, what have you, into a mono of a list of that same type. Yeah. Yeah. This is one of the, when we talk about reactive programming, sort of getting started with it, we say, sort of imperative programming has this learning curve, which is really easy, really straightforward. You just read every straight line, and then you start going to more complex things, and you start doing microservices, and you realize it sort of gets asymptotically complex, right? The composition of really, really complex things to do becomes nearly impossible except for the best practitioners in the world to do. And reactive programming goes sort of a bit differently. It's really hard to get started, right? Like, you take a look at this and you're like, how the hell did I know that flat map or flat map many or collect a list even existed? If you take a look at the flux type, I think there's over 80 methods on that particular type that you could execute. But once you figure out how each one of those works, adding arbitrary new complexity sort of flattens, right? Like, now all of a sudden it doesn't require an absolute expert to do really complex things. You just start stacking these kinds of operators together as you go to get the patterns you're looking for. Does this come back? So it's up to the database driver implementer to decide exactly how this particular thing happens. So in the Postgres world, for example, we just execute this, and then a bunch of frames come to us. And so in this case, we'll sort of do some back pressure to it and ask for, I think, like 128 rows at a time. And you can tweak that to make it bigger if you think your network configuration can handle more or less than something like that. So we basically make it as efficient as we can. We're only going to make one outbound call to the database, and some arbitrary amount of data comes back to us, but we use back pressure to guarantee that we don't get overwhelmed by that. So I had mentioned this idea of doing an insert that's a bit parameterized. So we can say, connection, this time I want to create a statement. You'll see $1, $2. You'll expect to see, named values in MS SQL or something like that. And this is where we do the binding, where we can say here, bind to that first parameter, the number 100, bind to the second parameter, the number 200, and then we'll see add. And the key thing that we're effectively saying here is add is sort of a carriage return. This is what I think the row looks like, and now I want to start on a new row. Bind again, bind again. So we're basically doing two different inserts, but because of the way sort of prepared statements work, we send this. We actually send a whole in the Postgres world. We send a whole block of data, bang, 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 and then we wait at the execute for it to start doing things and returning data back to us. So again, like hyper optimized, we send a huge amount of data, typically in one outbound request, and then we wait for the database to return to us. There's sort of an implicit there's an implicit add anytime you call execute, but effectively what you're looking at here is insertion of two different rows. But beyond just sort of the trivial examples that we've seen so far, we do also support transactionality. So now, before we do, say, a bunch of inserts, two different inserts like we see here, we want to begin a transaction, create the statement, insert, insert. Even though all of this goes as a single block of outbound data request, each one of those inserts would happen in their own isolated transaction. Call it auto commit. Right, is the way we typically refer to this in JDBC. So what we want to do is begin a transaction, do something, afterwards we'll commit that transaction, but if there's an error, I want to roll back this transaction and then propagate the error later on, right? I want to make sure it still gets out, but I need to roll it back. So now all of a sudden you start taking a look at this and you're like, this is pretty complex, right? This is non-trivial to write. So, remember, one of our design principles was this idea that the driver SPI contains the minimal set of operations that are implementation specific and nothing more. And especially for those of you who are old enough to remember actually ever doing this, this is basically try, catch, finally, try, catch right here, this block right here, if you remember that from how JDBC is supposed to work, right? This looks very much like that pattern because the pattern's correct. But no one actually writes this anymore because there's always been a client that takes care of it. So what we actually need is, on top of this SPI, a humane client of some kind. And in fact, what we actually need is a bunch of humane clients. Because I can't tell you how you want to do your kind of programming. Are you the kind of person who likes MyBatis and working directly with SQL on your own and doing manual mappings? Are you the kind of person who likes JPA? Are you the kind of that does its own ORM? Are you the kind of person who likes Spring Data repositories, where you just write an interface and all sorts of magic happens on the other side of it? So if we think about what a client might look like, in the R2DBC project there is sort of a demo client that I wrote. I don't really want to own this for the long term, but it's sort of based on the JDBI project, and it gives you an idea of what a humane API might look like. It might say, with handle, select something, straight map row. Just give you the row. Most of the time, nobody actually needs row metadata at all. We just know the name of the column we were going to do, and so let's just do a simple mapping out. Compare that back to what we saw with the driver SPI. An update probably looks like this, right? Again, just create update, do some bindings, execution. Realistically, nobody actually cares about what comes back from doing an insertion. How many people have actually ever looked to make sure the number inserted was a number they expected it to be? It's probably, I assume we just return a mono int from this. It's been a long time since I wrote this code. But most people just ignore it completely anyway. What about that example we had with the transaction and the try, catch, finally, try, catch? Hold on, did I go to the right slide? Yeah. It could be as simple as this, because behind the scenes, the client implementation can do that try, catch, finally, can do the delay until, connection commit, on error resume, connection.rollback, then mono error, right? It can do all of that for you, allowing you to focus in on your code. And if you're the kind of person who likes JDBI today, this API is really, really useful to you. Right? It's sort of kind of what you're looking for. But if you're a Spring Data kind of person, you like that sort of implicit, automatically generated repositories, you want something like this. Go find me all of the customers that have a particular last name, right? And you sort of manually write exactly what the select statement, the SQL statement is going to be, and it will figure out a way to do basic ORM to get your customer back, right? That's what now all of a sudden it looks a lot more like this. And so this is kind of this idea that we look at JDBC, and no one actually uses the JDBC API directly because they want something that looks like this, they want something that looks like JPA, they want something that looks like Spring Data instead, right? So any questions so far there? Yeah? Okay. So what about some of the alternatives? Actually, before we do alternatives, I wanted to pull up some real live code. It's one thing to sort of show what exactly this looks like, sort of really, really concise. But I wanted to show some more sort of complex examples. There is, in the R2DBC projects, there's this sort of example project, the example class. It's basically a TCK that we go through to show some of this. A lot of it is really parameterized so that we can run it against different databases that use different placeholders and stuff like that. But let's do... that is not what I wanted to do. What was it called? Postgres demo. So let's take a look in a little bit more detail. Let's see how high that actually is at what multiple insertions would look like. People in the back, is font size okay? You need a little bit larger? A little bit larger? Okay. Something like that. So in this particular case, we see that connection factory, we call create, a flat map many, and you can sort of see this idea of this is what it looks like in Postgres, the insertion, multiple adds like this. We do the same kind of thing where we're just going to do a connection closed as it finishes here. One of the nice things about using IntelliJ is it does actually show you all the things that you get, so we're getting a flux of PostgreSQL results from this. We're using a tool called Step Verifier that comes from Project Reactor. It just says, okay, I expected 5 things to actually come back from this. When I did insert, a flux of PostgreSQL results come back. 1 for each one of those insert statements. The result would tell us 1 row was inserted, 1 row was inserted, 1 row was inserted. You might want to see something a bit more complex, like how transaction management actually happens. So I'm going to sort of trim off the top of this, where we begin the transaction, and you start seeing this get glued together. Then many create a statement, execute it, pull out all of the values from that. We'll see a little bit further down. I don't think I can do collapses in here. We see that this comes out as that collection singleton list, right? So we saw, there was a question from earlier that we can just collect a list of these things. Next line, we'll go ahead and insert some more stuff into it, come back and get the rows updated. There's a step down here where we guarantee that the number of rows we expected was actually delivered into it. And then create another statement to do selection, committing the transaction, and guaranteeing that that stuff exists outside of the transaction. But again, what I'm showing you fundamentally here is this idea that this is sort of the driver SPI that you'd consider to be a bit inhumane. You might instead want to take a look at this one. So that same kind of thing, again, a little bit more parameterized than you might otherwise want, is the transaction, where we talk about executing something inside of the transaction, doing the selection and extracting the columns out, inserting some more stuff, making sure that those columns exist as it was, doing a commit and getting the data back out on the other side. Okay. So there's various levels of abstractions you should expect to work with R2DBC. Okay. So what about the alternatives? It is very common for people who are using reactive programming that want to use something like Spring Web Flux, but are hamstrung by the fact that JDBC is sort of a blocking API and therefore unusable, is to wrap JDBC itself in a thread pool. Now, this works sort of in the abstract, but the reality is, imagine you have a bunch of different requests coming in. in a thread pool. When you're backing a pool, you have to have a queue of some kind. There are two different kinds of queues. If you had an unbounded queue, you could effectively have enough requests coming in from the web tier that you explode an unbounded queue. It basically says, oh, I can't handle any, or I'm going to just keep adding, and queuing up, and I'll get back to you eventually until you've exhausted the heap. Alternately, because you don't want to exhaust the heap, you can have a bounded queue. But a bounded queue ends up leading to quite a lot of blocking, right? So at some point, your queue, maybe it's 1,000, 2,000, 10,000 elements that it's willing to accept. When you add that next element, this one of 4 threads, so literally 25% of the threads you have available to you, is just going to get blocked on the insert, right? It can't add it, at which point you're sort of stuffed. You've broken your non-blocking programming model, and you've immediately caused a huge issue because you're blocking one of the very few threads that you have. So that's one option. Most people, you don't want to use this kind of thing. It can't. Under any kind of load, you're likely to get yourself into trouble. There are other specifications sort of knocking around. Many of them are in similar or are in very early stages. Just recently we heard about a team out at Eclipse that is thinking about the same kind of problem. Fundamentally, they're all similar in design. We just happen to get a really good start. We've got the Spring team providing a lot of feedback. We've engaged a bunch of database vendors and them as well, and they've had a lot of say into ours as well. Those early stage other alternatives typically have a very, very small number of implementations, and it's quite likely when all of this is said and done that we're all going to collaborate together. There aren't going to be multiple specifications for reactive database access. So what can you do today? R2DBC itself is in the final milestones before a 0.8.0 release. In fact, at lunch today, I was supposed to have done a release, 0.8 M8. I didn't do it. I'll do it either tonight or tomorrow morning, depending on when we get the release notes finished. But what we're effectively signaling here is we believe that this specification is production ready and other vendors should start implementing it. And if there is an implementation like the Postgres or the MS SQL one, we believe that it is, when we hit 0.8 release very shortly, it is good enough for you to use in production. But all of this comes with a caveat. The reason it's not going 1.0 is we don't believe that the spec is completely guaranteed to never change in the near future, right? We'll reserve 1.0 when we believe that there are enough sort of client implementations and enough other database implementations to say this is good, this is completely stable. But we would say if you want to start experimenting with this, if you are the kind of company that has a really, really good use case for reactive programming, you can start taking a look at R2DBC and actually using it in production. We have sort of internally, so within the scope of the R2DBC project itself, implementations for Postgres and MS SQL, and we even have an H2 implementation for those of you who want to do testing sort of locally. And all of those implementations have batching support, extensive type conversions, so like typically 20 different automated type conversions. We just added blob and clob support, save points transactions, transaction isolation. In this latest milestone, we're adding both service-based driver selection. So if you're familiar, you'll just be able to basically say connection.getFactories, and it determines what's on your class path. And we've also added connection URLs. So much in the way JDBC URLs work, where you don't even need to know what kind of driver you might possibly be using. You're given an opaque string from your cloud service provider or something like that. We will go in a much more coherent way than JDBC URLs actually work. We will go and grab from your class path exactly the right driver type, and we will configure it and instantiate a new connection factory for you straight off. We have Spring Data R2DBC is easily the premier client implementation. I said we also have this R2DBC client, which is more programmatic version. It will also go 0.8.0 release. It is production ready. But I don't think I expect long-term for such a thing to exist. Realistically, it is a clone of JDBI. I'd much rather JDBI actually just integrate this stuff directly. We expect teams like the Juke team or maybe the Hibernate team working on what a reactive JPA might look like. but to be much more the client implementations, working at whatever levels that you want. We also have connection pooling, which is a very recent addition. I'm not sure how many of you know, but trying to do a sort of generic pool of any kind in a completely non-blocking and reactive manner, really, really difficult to do. The good news is we have the Project Reactor team. They've created Reactor Pool, which is sort of a generic thing, and we built our connection pooling on top of that. We also have, due to an absolutely amazing external contribution, observability. There's a project called R2DBC proxy, where a guy named Tadaya just sort of saw R2DBC, started a project, did it, and like we found out about it, like, hey, do you want to move that into R2DBC? And so now we have this really full-featured sort of proxying mechanism around the entire API. He sort of added some demonstrations around micrometer support, but it was all sort of a goal to bake observability into the spec from the beginning at the request primarily of APM vendors. The APM vendors, another group that are on that list of people who ate the JDBC API, they find it really, really difficult to do analysis and decorate it appropriately to find all the information that they need. So in this case, we're saying this is a first-class supported concept inside of R2DBC, and we already have, the Datadog team, the New Relic team, and things like that, looking at, making sure that we provide enough information at sort of this observability layer to make sure that you, as application developers, can get the information you want about performance. Safe harbor statement basically says you cannot hold me to anything I'm about to say because I'm about to talk about what's the future, right? The key for us is we want additional implementations on the database side. It's a real reason that we're pushing so hard for 0.8.0 release. We already actually have the MySQL team and the Google Cloud Spanner both in public, in repositories, have started work. The MySQL one is coming from a project called JSync SQL, which is sort of a native Kotlin implementation of Postgres and MySQL, two obvious databases, and they've gone off and started adding support for the API, Google Cloud as well here. We're talking to both the IBM team and the SAP HANA team about implementations there. They've, sort of started talking to us, but I don't believe there's any code there. We prefer long-term for the database vendors to own their own drivers. I may now be an expert in the Postgres wire protocol, but I don't want to be for the rest of my career. The Postgres team is much better at that. And so we have the Postgres team, sort of interacting, submitting PRs, coming to the calls and things like that. But in the end, this is all a bootstrapping to give them our implementation eventually. Same thing with the MS SQL. We want Microsoft to take that sort of over once they're convinced that there's a future into this. Same thing at a different level of abstraction. We want a lot more clients. You can did I really write JDBC? I meant to write JDBI. Yeah. It was a long flight from California. And JDBI have initial support here as well. They started taking a look at it, and certainly we're getting a lot of really, really great feedback, actually, from their maintainers about what we need to add to the SPI, what we can safely remove from the SPI to make sure that we deliver what they need to write those client layer abstractions on top of it. So finally, we've got a website, our Twitter account, GitHub is a place to go find all the interesting things. We've got a mailing list, and actually this is a reasonable thing for people in this time zone, finally. I present this in California quite a lot. Nobody's coming to a 6:30 on Friday morning weekly call, but we have a weekly call open to the public that anybody can join and sort of watch what progress is happening, raise issues if you don't want to go through the mailing list or GitHub issues, and sort of just get involved generally in the community. And so that's it. So let me first off say thank you for having me here, and I'll answer any questions anybody has. Yeah, here.
So, you're releasing it as 0.8.
Yep.
How long is it going to take to get to a 1?
How long is it going to take to get to a 1? That's a great question. We don't think it's going to take horribly long. I would say it's probably likely next year, but we sort of have a chicken and egg problem right now. It's difficult to enlist database vendors to start implementation and give us feedback if they don't think that this is something people can use in production, right? They're not going to go against an experimental thing. So we want this to be signaled as, we think this is stable. We think this is a really good idea. We want it to go out there. We want database vendors to start implementing it. We want client vendors to start building on top of it. But we also are aware that we likely have missed something, and we want your feedback. So if it turns out we have been completely in the wrong direction, who knows, right? It could be any period of time. But realistically, I personally, again, safe harbor statement, would love to see this go 1.0 next year, right? Maybe middle of next year. Spring I/O, DevOps UK comes around this time every year, so maybe it can tie into something like that. It's unclear right now, and it's totally dependent on how the rest of the community reacts to it. Yeah, in the back. Have I heard any word from Oracle? So this is in context to the fact that there is a project called ADBA, Asynchronous Database Access, which is sort of being run out of the JDBC team. We have talked with them repeatedly, and fundamentally, I think we in the ADBA team have a very different view of how this spec needs to go. They are focused almost exclusively on asynchronous database access. And as I said on that very first slide, to stress very strongly, Reactive is actually a step beyond that with this pull, push, back pressure kind of thing. And you can implement a sort of totally asynchronous API on top of a reactive API, but you can't implement a reactive API on top of just a purely asynchronous. You can't transmit back pressure through it. So we've sort of talked to them a couple of times. I sort of hold out hope in the long term that what our TwoDBC eventually does is influences the ADBA spec or a future ADBA spec. But even though the ADBA team has Java 9, as of Java 9, has like the Flow API, which is sort of the Java standard of the Reactive Streams API. They don't seem to be particularly interested in using it and doing that kind of back pressure. So I'm not optimistic that we will eventually come together, but again, like it sort of falls into this line here. Really early stages. When I say a small number of implementations for a long time, they only had an implementation that was ADBA delegating to JDBC in a thread pool, so all the problems of just using JDBC in a thread pool. Now they've got an Oracle one and no other implementation. So we're doing a bit better than them. But again, like I think ideally we end up in a situation where these two things come together in some way, but I'm not sure how that happens between now and then. It's a good question. Yeah. So the question is how our pooling avoids the pitfalls of connection pooling in JDBC. What kind of pitfalls do you see there?
You mentioned before, either having resource exhaustion.
Yeah, resource exhaustion or vice versa. The beauty of reactive pooling, because there is this idea, the beauty of reactive in that there is this pull-push kind of back pressure, right, means that given a connection pool of a fixed size, someone can ask for that connection, can ask for a connection out of that particular pool, and if there is not one to give, it doesn't actually block anything, right? It just says, I am going to subscribe to your publisher, and when I'll request, hey, go give me one, and only when you are ready to give me one will one come back to me. So there isn't really a resource exhaustion issue from that particular side. You may get some resource starvation, potentially, right? Because a connection, we can't break sort of the fact that most databases use, I don't know what the opposite of multiplexed connections would be, monoplexed connections, and it can only be owned by a single request at any given time and then has to be returned to the pool. You can't mux a bunch of requests over it. So if you are connecting to a database that only allows, 64 connections to it or something like that, there can only be 64 things in a pool. We're just in a better situation where when you are waiting for it, you're not occupying a thread doing that thing. And so other things can come in, requests come in, and it's totally possible that you end up, stacking up, 1,000 clients all waiting to get a connection to do the thing against the database, but they don't occupy 1,000 threads while you're waiting. Yeah. Good. One last question here. What changes do you need on the server side? Zero. Right? This is one of the things that has been like the biggest eye-opener to me. I always assumed people who wrote JDBC drivers were basically like right up there next to compiler authors as far as understanding these really technical things. It turns out the wire protocols these databases use, not very hard, right? You just need to know, and you need to understand how to go through byte buffers and byte counting and these sort of packed binary kinds of things. But anybody can understand these wire protocols. And ideally, you have a wire protocol that does sort of pull push back pressure like Postgres does, but MySQL doesn't have this. MS SQL, I don't think, has this. The author of the drivers back there could prove me wrong. But so if we could take advantage of it, we can, but if not, we just use what the wire protocol is there for us. One of the things we'd really, really like, and it's sort of a bleed over with my work in RSocket, is I would really like database vendors to do multiplexed connections. So you only need a single physical connection into the database that you can do a bunch of logical connections over it. That would require database side changes, and we've raised it to the Postgres team, and they're sort of thinking about it for Postgres 12 or 13 as a possibility. But in general, we can implement an R2DBC driver on any existing database protocol that exists today. Great. Okay, so thank you all again. Call it here. If you have any more questions, feel free to come up and talk to me.